Before we go into the shortcut for identifying the starting material or how to attack these problems that, yes, both involve aldehydes and ketones, we have to take a step back and learn and review the basics. First, a review from organic chemistry. Let me know in the comments if this looks familiar. The two molecules we're looking at today are the aldehyde and the ketone. And the reason we talk about them together is because they kind of look like each other and their chemistry is very similar. If I have a molecule that looks like this is an aldehyde. And if I copy this molecule and make the other thing look pretty much exactly the same, but instead of a hydrogen, I extend it out. So I have another methyl group in this case, that is a ketone. The aldehyde in general is an R, a carbonyl, that's this thing, a carbon double bound to one oxygen, but a hydrogen at the end. And the ketone is an R, a carbonyl, and another R group, which could be the same or different. Here I have something different. The way that I remember it is the ketone does not want to be alone. So it's not alone at the end of the molecule like the aldehyde. It is in the middle, surrounded by carbon. The way that you name an aldehyde or a ketone, again, this is a quick fly through from what you should have already studied in Organic Chemistry 1. The aldehyde gets the ending Al. And so what we have here is 1, 2, 3, 4. 4 carbons for a first name of bute, only single bonds in the parent carbon to carbon single bonds, ane. Al for the ending, but that means we drop the E, Al for butanal. You don't have to put a number because the 1 is self-understood, given that it's terminal. For the ketone, we do have to specify a number because it can show up at any part in the middle of this molecule. And so we say that the carbonyl is on carbon 2. 5 gives me a first name of pent, only single bonds in the parent chain. And the ending is ONE, so pentanone. So we have butanol for the first one, 2 pentanone for the second one. Give me a thumbs up in the comments if this is familiar and if you're with me so far. And a good mnemonic here from Jackie. Another way to remember the aldehyde is it's an aldehyde with a hydrogen. I love that because that'll help you remember the H in the aldehyde compared to the ON in the ketone. So thumbs up in the comments if you're with me. And let's see what we really have to know. If there's only one thing you take away from this session, this is what I want you to take away. The carbonyl, regardless of what else is attached to it, meaning if I have an R group on either side or if I have a hydrogen for the aldehyde, the carbonyl is what we're looking at. We have a C double bound O with the 2 lone electrons on oxygen. Carbon is less electronegative than oxygen. Oxygen wants to borrow or steal or pull or whatever you want with those electrons. That gives me a resonance structure that still has the carbon bound to oxygen. But these electrons that collapsed up from the pi bond, that's a third lone pair for a negative charge. This was a ketone because I had 2 R groups. Carbon now only has 3 bonds. Here it has 4. That means it has an incomplete octet. It's not very stable. And it gets a carbocation because it's missing a bond. These are 2 contributing resonance structures where the major is the one that has no charges. Charges are not ideal. And the minor has a separation of charge. Now, this is typically what you see, but this is important to understand because the resonance hybrid, that in between of the 2, looks something like this. My C, single bound O with 2 lone pairs. In this case, we'll have the 2 R groups. That pi bond is kind of going up and down between oxygen and carbon. So that negative goes between negative and neutral for partial negative. This goes between positive and neutral for partial positive. And the fact that carbon is partially positive, this is what makes the carbon so susceptible to attack. And this is where we get not just this chapter for aldehydes and ketones, but you're going to see the same thing with your carboxylic acids, carboxylic acid derivatives, basically everything that has a carbonyl. So if you didn't have it clarified like this in class, because it's so important, I want to see smiley faces in the chat to let me know if this finally makes sense, because this is going to be the driving force behind everything we talk about today. And since we're talking about nucleophilic attack, let's see what that looks like. And today we're just going to cover aldehydes and ketones because we won't have time for everything else. But yes, Scotty, knowing the logic is going to make this entire chapter so much easier because it won't be a million different reactions that you're memorizing. It's going to be one pattern that you simply see over and over, depending on what it is that you have. If I already know that my carbon is partially positive, bringing in a nucleophile that is negative or partially negative reminds me that, well, not reminds me, you should recognize that the nucleophile wants to attack at the carbonyl carbon, at that partially positive carbon. These electrons already want to go up, and so in this case, they have to, otherwise carbon would have too many bonds. What does this result in? Carbon is now single bound to oxygen with the 2 lone pairs that it had before. It now gets that 3rd lone pair from these electrons that collapsed up. That's a full negative charge. I still have my 2 R groups attached, so let's not forget them. Let's push this one slightly out of the way. And now that leaves room for the nucleophile that just added for my intermediate. Now, the next step in this reaction is typically going to be a protonation or some kind of take care of that oxygen. But for now, this is the gist of it. This is a summary of most of the reactions I'm going to teach you today. Looking at the starting molecule, my nucleophile, the carbon here is sp2 hybridized. If you remember, sp2 means that it's trigonal planar, or in simple English, flat. That means it can get attacked from the top or from the bottom. But if you look at the product, this is sp3 hybridized, and sp3 is 3-dimensional. It is tetrahedral. That means if my final product is chiral, which it will be if the R groups are not the same, then, and the nucleophile can also not be the same because you need 4 unique substituents. If chiral, the product will be racemic. That means I'm going to get a 50-50 mixture of R and S because of the fact that I started with something sp2. Stereochemistry, slightly less important. The overall reaction, the nucleophilic attack, that is crucial. That is what we're going to look at with all the reactions today. But first, some questions will use a non-carbonyl starting molecule. And so instead of, here's a synthesis product that you have to create starting from an aldehyde or ketone, you may be asked to start with a completely different kind of molecule. Professors, especially in Orgo 2, and let me know if your professor does that, will take what is supposedly an Orgo 2 reaction. It has 10 steps, and only 2 of them will be Orgo 2. 8 steps will be organic chemistry 1 that you somehow have to remember. So let me know if your professor likes to do that. And if they do, you have to know how to create that aldehyde or that ketone. You have to know how to make that carbonyl from a different starting molecule. I see a question here. Does carbon get a charge after the double bond breaks? I don't know why I'm blanking on this. That is a very good question. I don't want you to memorize it. I want you to think about it. Carbon would be a carbocation if the formal charge is not 0. And the way you do the formal charge, the calculation that I like to use is should minus has. It should have 4. It has 4. Or just look for 4 bonds. Here I have a total of 4, 2 to the R group, and then a double bond to oxygen. Here it also has 4, 2 to the R groups, a single bond to oxygen, but the nucleophile also took a bond. In fact, when the nucleophile attacked, this got kicked out, but the total never changed. The reason it got kicked out is because you would have had 5 instead of 4. But if we look at the resonance, just the resonance itself, here, well, actually not that one, here you have a formal charge of +1 because carbon here only has 3. Should minus has, 4 minus 3 is +1. So very good question, Scotty. And if anyone else was wondering, let me know if that is clear. Can you explain what's in orange? Which part? So the hybridization of the carbon is what I'm looking at. This one is sp2, it's flat. This one is sp3, it's trigonal planar. When the attack happens and you make that bond to a 4th group, the nucleophile, you go from flat to three-dimensional. And that three-dimensional can be in the R or S, depending on where the attack comes from, top or bottom, and of course, depending on what else you have there. Scotty, awesome. My professor loves doing that. Well, you are absolutely going to be prepared. Shed minus has is such a good way. Yeah, so my formal charge shortcut is something I created when I saw what was the number of bonding electrons. No, half the number. You know what? I don't even remember the formula. Who cares? Should minus has for your formal charge, and you are good to go. And I have a video on that if you want to see it explained in detail. So let's see how to make the aldehyde or the ketone. I don't know why I wrote half of one word and the whole of the other. Aldehyde or ketone. And we'll start with just a quick Orgo 1 review. There is one reaction that you learned in Orgo 1 that is your go-to for making aldehydes and ketones. And that is starting with which molecule? Starting with an alkyne. We can start with an internal or a terminal. I will use a terminal because I want to show you how the two different reactions differ. You should remember that the hydration of an alkyne, and hint, hint, if you forgot how to make the alkyne, go back to my synthesis session because I show you how to go from either an alkane, an alkyl halide, or a double bond to get to the alkyne. But if we try the hydration reaction, we have two different options for two different alkynes in this case. The first one is oxymercuration. Hg is mercury, so the mercuration, that's the Hg. HgSO4 and H2SO4 and water. This is an acid catalyzed reaction. What happens, just like with the alkenes, we break one pi bond. That gives me a molecule that looks like this. Only one pi bond is broken, the other one remains. This one follows Markovnikov's rule. I'm just going to write Mark's rule because his name is way too long. And puts an alcohol at the more substituted carbon. If, on the other hand, I react it with some version of boron, typically I've seen here is B2H6, but you'll see BH3THF, 9BBN, anything with boron, that's the glue. Hydroboration, boron, boration, that's the B. That's step 1. Step 2 is NaOH, H2O2, and sometimes you'll see H2O. Professors don't necessarily include that. You break one pi bond, just like with the alkene, and you get an alcohol added to the anti-Markovnikov position, the terminal carbon. And I'll just put anti-mark here. All right, now this chapter, this session, is very clearly called aldehydes and ketones. But what I just gave you here for the product is neither an aldehyde nor a ketone. So what is going on? What I have here, and this is crucial for now and in the next chapter, you're going to learn this mechanism in detail, so make sure you understand. I have an alkene and an alcohol on the same exact carbon. This thing is called an ene for the alkene plus an ol for the alcohol, an enol, and this is a terminal enol. This is not a stable intermediate. Therefore, in the presence of an acid or a base, it will automatically isomerize, or the technical term is tautomerize, to give me as follows. And let me know in the comments if you know the kind of isomerization reaction that this is. Here's what happens. Look at your alkene. Here's the shortcut. You take your alkene, cancel out the hydrogen, put a pi bond, hydrogen on the other end of the alkene. What does that look like? Well, actually, I'm sorry. You also have to, let me show that to you again in order so you can do the shortcut quickly. Break a bond, make a bond. Break a bond, make a bond. Let me know in the comments if you recognize this pattern from a previous session, because this is a very, very common. All right, so what did I do? I had my O, but I crossed out my H. I made a bond, broke the pi bond, made a bond to hydrogen, which I don't have to show, but I'm going to show it to you here just so you see what happened. And let's do the same thing for the terminal. Break a bond, make a bond, break a bond, make a bond. And what this gives me here is that O with now a pi bond. I need to do that in red. with now a pi bond and a hydrogen. And that is why this is an aldehyde and ketone reaction, because the internal one, the oxymercuration, gave me a ketone, and the terminal hydroboration gave me an aldehyde. I see, oh, I don't see it. So what I was looking for here is KET for ketoenol tautomerization. You don't have to show the mechanism unless your professor specifically asks for it. You do have to write KET, and I'm going to put this in brackets because this is not isolated. It will go right there before you have a chance to realize what happened. And so your final product is alkyne to ketone, alkyne to aldehyde, no isolated intermediates. If you're with me so far, let me know, and let me know if you have any questions. Would BH4 work here? That is a very good question. So you are referring to something like NaBH4, and the answer is no. What makes the NaBH4 so reactive that we're about to look at is the fact that it's BHHH, technically a BH3, just like what we have here, but then that H4 is really just a hydride, and this entire thing together is BH4 minus. We're going to look at that shortly. So I love that you brought it up because that's a good lead-in. Yes, during the Diels-Alder, Jackie, I'm very proud of you. Make and break is a very common pattern for here, for Diels-Alder, for pericyclic, so many reactions. The intermediate is not stable. Absolutely. Wait, isn't the top an aldehyde too? No, be very careful. I put that hydrogen only to show you that it moved over there. But notice there's a carbon to carbon bond. So this right here is another hydrogen and another hydrogen because it's a terminal group. Nice. So proud of you. I love when students tell me things like that. All right, so this is a definite Orgo 1 reaction. The next one that I want to talk about, redox, is typically covered in Orgo 2, but some students already learned this in Orgo 1. So we'll do a review, an overview just in case. If I have a primary alcohol, actually, before I go into it, let's talk about what redox is. Redox is oxidation and reduction. And the mnemonic that I like best, I learned this from one of my students, because I learned oil rig. I don't feel like it works. But this one, Leo the lion says, grrr. That one I like. Let me see a lion emoji in the comment if you like my growl. Actually, subscribe if you haven't yet, because I'm trying to reach 1 million subscribers, and I would really, really appreciate your help. So Leo the lion says grrr tells me that loss of electrons is oxidation, and a gain of electrons is reduction. Now, if you're looking at this thinking, wait, this is organic chemistry class, why are we looking at electrons? We're supposed to be looking at atoms. It does not appear to be that helpful until you remember that an electron, whoops, that does not look like anything. An electron plus a proton is a hydrogen atom. And so if we translate this to loss of a hydrogen is oxidation, gain of a hydrogen is reduction, hydrogen is reduction. Oxygen is the exact opposite. And so oxidation would be a gain of oxygen is oxidation, a loss of oxygen is reduction, and there you have your antagonistic pairs. If I gain hydrogen, it's reduction. If I gain oxygen, it's oxidation. And for these reactions, you do need to know how to go back and forth. So I will take my starting molecule, starting with a primary alcohol. If I have a primary alcohol and I do 1 round of oxidation, and your oxidizing reagents, these are reagents you have to memorize, can be anything with, excuse my language, a shitload of oxygens in them, like Na2Cr2O7, KMnO4, O3 with other things. Just think of all those oxygens. That's how you know oxygen oxidation. That primary alcohol will go to an aldehyde. I made 1 extra bond between carbon and oxygen. But if I oxidize it again, I make it undergo another round of oxidation, what'll happen is from having 2 bonds to oxygen, I get a 3rd bond to oxygen. And by the way, I also get a hydrogen. So I'm starting with a primary alcohol going to an aldehyde going to a carboxylic acid. And I'll just put carboxy for the sake of amount of space. If I reverse the reaction, same thing. I cut 1 bond from carbon to oxygen. So I have 3 bonds carbon to oxygen, 2 bonds carbon to oxygen, 1 bond carbon to oxygen. If we look at the oxygen perspective, if I look at the hydrogen perspective, notice that carbon and oxygen here have no bonds to hydrogen. 1 bond to hydrogen. I reduced it. I added 1 hydrogen. And it's specifically hydrogen on the carbon. And if I reduce it again, that was supposed to be an arrow. If I reduce it again, now I have a 2nd hydrogen. 1st hydrogen, 2nd hydrogen. So oxidation and reduction are just opposites of each other. Your oxidizing reagents have lots of oxygen. Let me know in the comments which one you've learned. Na2Cr2O7, KMnO4. These are 2 common ones, so I'll just put, there's so many. A lot of them have some version of chromium and a bunch of oxygens. And for reduction, because reduction is hydrogen, well, they're going to have lots of hydrogen. For example, lithium aluminum hydride, 4 hydrogens, or sodium borohydrogens, again, sodium borohydride, again, 4 hydrogens. This is also called LAH, lithium aluminum hydride, LAH. If you just memorize these, you will be fine. Primary goes to an aldehyde. But what if I start with a more substituted alcohol? Let's keep that in view. If I have a secondary alcohol and I oxidize it, I will add bonds between carbon and oxygen. So that will give me, I have this right here. I lose that hydrogen, but now I gain a pi bond right there. So there was a hydrogen there, and I lost it to oxidize. If I try to oxidize it further, there's going to be no reaction because there is no more hydrogens to remove. That's another thing I should point out. We have 2 hydrogens that we can remove, 1, 2 levels of oxidation. 1 hydrogen to remove, 1 level of oxidation. And then reduction will obviously undo it in the same way. And so the ketone has no hydrogen on carbon. Reduce it, you have 1 hydrogen on carbon. Let me know in the comments if the patterns make sense. Question about it earlier. I always get confused on Markovnikov, anti-Markovnikov. Is there a hack to identify when I'm supposed to use it? Taylor, my hack is based on logic rather than memorization. If you go back to the mechanism and see carbocation intermediate, that has to be more stable, therefore Markovnikov. No carbocation intermediate, there is something else that drives it. And I explain this in more detail in the Markovnikov video. Email me if you need the link, if you can't find it on your own. Yes, I will definitely talk about that because we have to. That's what I was thinking of. Let me know what specifically, because I didn't see when you put that in. Wait, so the secondary carbon lost 2 hydrogens? No, the secondary carbon only lost 1 hydrogen. This right here is a secondary alcohol. I'll just put secondary OH. And that goes to a ketone. This one was a primary alcohol. So in the first reaction, it lost 1 hydrogen. Let me make 1 purple and 1 red. So in the first reaction, we lost the purple one. We still have the red one. You lose the red one, you have nothing because you've got an oxygen right there. Let me know if that makes sense. How does NaClO oxidize so effectively? It has to do with the reagent itself, not the fact that it has so many oxygens. But the way I look out for it is I'm looking for the oxygen. So notice these 2 have no oxygen in them. They have hydrogen for reduction. Typically, you do enough practice, you will have memorized the right reagents. But if sometimes you get stuck, is this oxidation or reduction, look for the O versus the H. So I have oxygen, oxygen, hydrogen, hydrogen, and hydrogen. I guess, I mean, it seems like the OH lost this hydrogen. Yes, so we have to make a pi bond, and that means we have to lose a hydrogen off each. So we lost a hydrogen here and here to make that pi bond. And then over here, because we're not making a triple bond, it's simply breaking this hydrogen off and bringing in an oxygen and a hydrogen. Now, this is not the same hydrogen. This one was lost, and a different hydrogen was brought in at the last step. You're going to learn this mechanism in detail. Well, I don't know which chapter, but definitely in the carboxylic acid chapter. The NADH4, yes. Okay, so we're on the same page. Excellent. I haven't done the mechanism in a while. That's fine. Anything that I bring up in a session that you know you have to review from the past, that is your clue. Make a note. I need to review this old reaction so that whatever your professor throws at you, you will be ready, because I caught you off guard today and not on Friday, on your exam's Friday, right? So not on your exam. All right, now, what if you want to completely reduce this thing? So what if instead of going from a ketone to no oxygen at all whatsoever, this is a reaction that is kind of brought up briefly in the chapter on benzene reactions, electrophilic aromatic substitution, nucleophilic aromatic substitution, but professors don't take the time to explain it, and then they expect you to remember how to do it. So if there was a reaction, here's the scenario. You need a directing group that will do meta-directing, which is what this is going to give me, but you need your final product to not have a carbonyl. If I started with this, this is an ortho-para director. One trick, one way around it is to start with a carbonyl, do the reaction, add whatever it is that I need to add, and then just completely cut that carbonyl off. And you have two options. The first option, well, let me show you the products first. The product is, well, very simple. I just cut the carbonyl off. But which direction I choose, and I know your professor probably said it was arbitrary. It is not. I can choose, let me know if you know the name of this reaction, either ZnHg with HCl. That is supposed to look like an H. Or I can choose to do something like H2NNH2. You'll also see this written as NH2NH2. You'll also see it written as N2H4, whatever. It's all the same thing. H2NNH2 in KOH. The difference in knowing when to choose the reaction is very simple. The Clemmensen reduction, that is this one, and I always spell it wrong. I think it's spelled like this, Clemmensen, not Clemmensen. Clemmensen, and this one is Wolff-Kishner. Look at what is going on in each case. HCl is under acidic conditions. Clemmensen has KOH, that's under basic conditions. If you have a carboxylic acid on your molecule, please don't use Wolff-Kishner. You're going to deprotonate your carboxy group. Use Clemmensen. If you have a base, use the Wolff-Kishner reduction. So that's the difference in deciding which one. If it doesn't matter, then pen and paper doesn't matter. I'm sure one reagent is more expensive than the other, but it's not costing me any different to write it out, so I'm just going to use both. Let me see a mind-blown emoji if your professor did not clarify this in the EAS chapter, but if you now feel confident using this in your synthesis arsenal. Wouldn't the secondary alcohol go to a carboxylic acid? If I try to turn the ketone into a carboxylic acid, it would look something like this, but then I have to add another OH. The problem here is that carbon has 5 bonds, and that's why it cannot happen. That's why this is a no reaction, because I have no other hydrogen to remove. Here, after I removed the hydrogen, or I guess this one first, and I got an aldehyde, I then have another hydrogen to remove to go all the way to a carboxylic acid. So that's a very good question. Let me know if that makes sense. Definitely did not. Well, now you know it, and you'll be able to use it. So let's go into the mechanisms for brain fart there, aldehyde and ketone reactions. So we talked about the fact that the mechanism is a carbonyl getting attacked by a nucleophile and the electrons getting kicked out. We'll start with a weak nucleophile using something like water or alcohol, which is essentially the same thing. It's just the difference between the R group and a hydrogen on an OH. So the first one, let's start with a very simple molecule. We'll have a ketone reacting with a strong base, NaOH. This is the hydration reaction. If it reacts with NaOH in the presence of H2O, Na plus is a positive spectator, so we get rid of it. OH minus will do a nucleophilic attack right there at the carbonyl, kicking up those electrons. This gives me, as we saw before, oxygen with 3 lone pairs negative, and the OH now attached. This happened in basic conditions, so technically it stops here, but I don't want to have a negative for my final product. And so after I know the reaction is done, I'll bring in some water in a mild acidic solution, so something like HCl, but very dilute. This will allow the oxygen to grab a hydrogen, give this back its electrons. Actually, what am I talking about? This happens in water. I don't need the HCl. If it happened in HCl, I'd be using H3O+, which you can also use. You just want to go very, very mild so you don't destroy the reaction. And that will give you the oxygen, the green OH that we added initially, and now the blue OH for diol. Di for 2, ol for alcohols, a diol. Now this thing is not very stable. That's why I said be careful with adding too much of a strong acid. But this is the reaction in base. If I do this reaction in acid, I would get the same exact product. And in acid, I would simply use something like H3O+. Before we look at the mechanism, I want to show you something very similar. So type backpack if you want to see the trick to instantly know how to do this reaction for this mechanism for a completely different reaction. And I will start breaking it down. So backpack in the comments if you want to see it, because it looks something like this. If I have a molecule of water, what I really have is a nucleophilic oxygen. That's my nucleophile and its electrons. This right here is a hydrogen 2-deprotonate. This right here is just a backpack. And if it's a backpack, I can put whatever I want into that backpack. My son is 3, and we got him a backpack for school. That backpack is almost as big as he is. So it's the funniest. He wears it, it just sits on his entire back. That backpack can be an R group. So hydrogen, small backpack, that's me wearing his backpack. Alcohol, that R group, that's a big backpack. That's a 3-year-old wearing a backpack that is about as big as he is. And so if I take this reaction, let me copy this thing, and I want to show you something. And now, why did it go there? I wanted to go with me for a moment. So I will take this reaction, but instead of reacting it with NaOH, I am going to swap the H for an R group, and we'll make that R CH3. Notice that, actually, let me show you in a fun, tricky way. Let's do it like this, CH3, OCH3, OCH3, and this right here, hold on, where am I? Right there, OCH3. Look at that. We just did the mechanism for, and this should be an alcohol. So that H2O, let me rewrite it, is HOH, that's H2O, is now a CH3. What do you think? Mind blown for this? I just did an entire mechanism by simply turning my H into a CH3 by applying the backpack trick, and we did the same exact thing, except This is no longer called a diol because it's an ol and then an ether, a completely different kind of molecule. And you absolutely have to know what this molecule is. This thing is part of the family that we call acetal. Now, professors will kind of teach the acetal, kind of not teach the acetal, but I want to show you something. If I start with an aldehyde and I react it with an alcohol, so pay attention to the colors that I'm using, ROH, that aldehyde is going to react the way I just showed you, where the O gets the H, and then the OR right there gets added. I don't know why I put it like that. So just ROH. The shortcut for showing this product is very simple. Break the pi bond, put a hydrogen on the oxygen, and put the OR group right there. That gives me my first step, my intermediate. If I react it with another ROH, then this right here, we just copy it the same way, except that OH group is completely gone. And in its place, I have the purple OR from the alcohol that came in. And then in solution, I have the hydrogen from the second one, and this entire thing that came off as a leaving group, O and H. So a water molecule off in solution. This right here is called an acetal. The half acetal, where it's half for the acetal OR, but half from a diol OH, this is called a half acetal, but it's called hemiacetal because that's a way nicer way to say it than half acetal, coming from an aldehyde. If I'm starting with a ketone, and professors tend to not explain the difference, let me know in the comments if your professor didn't. If I take this thing and I turn it into a ketone, how do I turn it into a ketone? I turn that into an R group right there. Then I just turn this into an R group and this into an R group, and the reaction is exactly the same. But because I started with a ketone, this is called a half a ketal or hemiketal, and this is called a ketal. So the difference between the acetal and the ketal is acetal starts with an A for aldehyde, and the ketal, K for ketone. That's the difference. But professors are going to mix it up because professors do what professors do, and they are going to call this an acetal. Let me know in the comments if I'm wrong. That is not an acetal. So why do they call it an acetal? Very simple. The entire class of this functional group is the acetal, and within acetal, I have acetal and ketal. So the way I like to think of it is if I'm talking about different categories or species or whatever genus phylum thing, if we talk about feline, I know I'm talking about cats. That could be a kitty cat, a lynx, a lion, a tiger. If I talk about canine, I could be talking about any type of dog. And if I talk about man, I'm not saying male human. I'm saying man is a human being. And the difference between a feline and a canine and a man could be that the man category includes a man, a woman, a child, which could be a man-child or a woman-child. So man is just the big picture. Acetal is the big picture, but the difference is the actual acetal, the actual man is a male, the female is a female version of man. Let me know if that makes sense because I see at least one confusion. So Taylor, tell me exactly where you're confused so that I can clarify. Yep, my professor did that. Yep, same. I watched your video today, like a breed of dog almost. Yeah, there you go. So the breed of acetal is an acetal or a ketal. It's like a square is a rectangle. Oh my goodness, I tried explaining this to my 3-year-old. No, mommy, that's not a square. That's a rectangle. Like, okay, kid, we're gonna agree on that today. Jackie confused about the backpack part. So Jackie, not Jackie, I'm sorry, Taylor. when I do this reaction, if I have an OH minus do the attack or an OCH3 minus do the attack, the mechanism is exactly the same. And the only difference is that in the OH mechanism, where I had an H, an H, an H, in the OCH3 mechanism, it's a CH3 and a CH3. Let me clean this up a little so that the notes make more sense when you look back at it later. So we have an O, and then attached to that we have a C, H3. So right there is your OR group that got attached, which is just the same exact mechanism as if the OH got attached. All right, so Taylor, thanks for confirming. Let me know if that makes sense. My kid is hilarious, except at 5 a.m. when he did not want to go back to sleep. We had a rough night, to say the least. All right, so for the mechanism for the acid catalyzed is slightly more involved. This was the quick mechanism because we used the base. The acidic reaction is reversible, and I'm going to show it to you for the acetal mechanism specifically. This is a reversible reaction. If I accidentally put a one-way arrow instead of a double-headed, because I do that very often, I want you to catch me because I want the notes to be correct when you're reviewing it later. Again, if you want a copy of today's session notes, make sure you put live notes in the comments and I will link it to you. I also forgot to tell you, brand new aldehyde and ketone practice worksheet. Just put worksheet in the comments and I will give you a link. Yes, even if you're watching the recording, the link will be automated so that as soon as you go to that link and sign up, it'll come to you right away, no matter when you're watching this, assuming the internet is still alive. All right, let's see. Thank you so much. That is awesome. Oh, wow, good luck. That is not an easy exam. So let's look at the mechanism. Type deal in the comments if you were going to keep me honest with regards to the double arrow for the reversible mechanism. And let's look at what happens when I react this in an acidic solution, whether I use an alcohol or water. I will use an alcohol in this case. The first step is the acid catalyzed, well, the acid catalyst. We looked at the nucleophilic attack before and we formed an O-. That works in base. I absolutely cannot form an O-, a negative oxygen in acid. If there's nothing else you take away from this part, from this mechanism, except for this, you're already ahead of the curve. Never, ever, ever, ever. My son learned to say that. Mommy, never, ever do that again. Never, ever, ever put an O- in an acid catalyzed reaction. And the way you're going to protect against the O- is the activation step. That activation is using the acid catalyst. Another reason we need to activate is the acid catalyst has a neutral attacker, and that is not strong enough compared to the O-. By adding an H+, we're making the oxygen positive. The oxygen is electronegative. It's greedy. It grabs those electrons, but the moment it does so, it has regrets. And so it starts pulling on the electron density between itself and carbon, making the carbon even more partially positive, making it susceptible to attack. And that is where the mechanism officially begins after the activation step, where we have the carbonyl gets attacked, these electrons kick up, and that gives us our next step, which it's about to get crowded. So let's redraw this slightly. I have my carbon chain. It has one oxygen bound to a hydrogen. One oxygen bound to a hydrogen no longer has a positive charge. We have the blue hydrogen that was there to begin with from the aldehyde. And then now we have, you know, let's switch their directions because that'll make life easier. And then I have the O, H, and CH3. Now the green oxygen has a lone pair positive charge. This is where I get the most questions regarding the next step. The next step in this reaction is when I have a proton transfer. I can do this in one of two ways. I can either bring in something from solution, another HOCH3, to grab that extra proton, giving it back its electrons. At the same time, I have another CH3. Oh, remember, it's an acid catalyzed solution, so some of them are protonated, lone pair positive charge. At the same time, I can also show this one getting grabbed. So this gets protonated at the same time that this gets deprotonated. Option 2, and some professors will let you do that, I prefer option 2, is an internal proton transfer, where instead of this oxygen grabbing a hydrogen from solution and the solution grabbing this hydrogen, just use this oxygen to grab that one. Save the middleman. No need for another intermediate, just a direct grab. This, I think, is what more professors ask for, so I'm showing you the 2 steps in one. And that will give me an intermediate that looks like this. Let's try to make heads and tails of what just happened. This one got deprotonated. This one got protonated. I'm using light blue to show this change. And this one is no longer positive because it lost the hydrogen, but this one is. So what we did was we took the hydrogen, we transferred it over, and in doing so, we also moved the positive charge. This is key. Now, a lot of students ask, well, what happens if I, actually, let me hold off on that question. Let me show you the next step first. This right here with a positive charge is a very good leaving group. And what does a good leaving group do? It leaves. The way that happens is this oxygen hasn't learned its lesson. It's still greedy. And so it will collapse the electrons down towards the carbon, forming a pi bond, kicking this one out. What I get as a result here, and this is where you want to pay very close attention, I have my carbon chain with a hydrogen. I have my OCH3 over here, double bound, and then the double bond is here, lone pair positive charge. I reformed my carbonyl, and in solution, I have an O, an H, and another H. This is a very confusing mechanism. Let me know if you're still with me, because we're still going strong. We're not quite there yet. But first, the question. So students will ask, Leah, why does the OCH3 go down? What happens if the OH is the one that chooses to go down? So if the OCH3 collapses down, water gets kicked out. But if the OH goes down, the alcohol would get kicked out. What stops that from happening? Let me know in the comments if you know what stops that from happening. The answer is absolutely nothing. It's a reversible reaction. When this goes down and alcohol is kicked out, they go back to here. When this goes down and water is kicked out, then we go forward. Which one ultimately happens? It goes back and forth, over and over and over, but eventually it will be whatever the solvent is going to keep attacking until you have all of the water kicked out and all of the alcohol having added. I remember my teacher said I couldn't do that. So if your professor said not to do the internal transfer, then show this and maybe show it in 2 steps. I showed it in 1, but you should show it in 2. One with the Friedel-Crafts reaction. If you're adding to the aromatic ring, so not related to this, but if you want to put more substituents in your aromatic ring, that's when you would use it. Scotty, go ahead. Questions. Keep throwing in those questions. I like to make sure to pause for a breath every now and then and read your questions. So this right here is still activated, just like the starting molecule. And because we have more alcohol in solution, the same thing happens again to kick that up. And what we get as a result here is my carbon chain. Let's move that out of the way. My carbon chain, my OCH3 now has just a single bond again because the pi bond broke. Wow, I'm losing my ability to speak here. And then I have an OCH3 and a hydrogen, lone pair, positive charge. Oh, you see, I did a one-way arrow. You got to catch me. That's reversible. Did I cut out for a moment? What's going on? Because sometimes my computer shuts off. So let me know if you guys lost anything along the way. The last step in this reaction is to bring another solvent molecule to deprotonate it because we want it to be neutral. I know this was a long reaction, so if you're overwhelmed right now, here's what I want you to do. Promise me that as soon as you get the notes, you are going to practice this over and over until you feel confident. Write it out 3, 4, 5 times if that's what it takes, because I want you to be crystal clear on this. We have our OCH3 that got deprotonated, the blue hydrogen from the aldehyde to begin with, and there we go. That is the acetal, and it's neutral. Could you just clarify what is happening in the third structure with the 2 different pathways? I got lost. So the third structure, I took a shortcut here. Let me show you. Let me see thumbs up in the comments if you want to see me expand this, because I think I may have confused students doing that. So let's expand the proton transfer over here. What I had was a molecule that looked like this, where I have an OH and an OCH3. The OCH3 is the group that just came in. The OH is the group that I need to get rid of. And the way that I do that is either an internal proton transfer, or I bring in a solvent molecule. CH3OH is going to grab, what's the oxygen specifically, grab a proton, give it back the electrons. That will give me, I'll have to copy most of that. I'll just clean it up after. That'll give me something that looks like this. Now they're both neutral. The next step is, well, there's hydrogens floating around. Where are they floating around? Sitting on more molecules of CH3OH because it's an acidic solution. This one can grab a hydrogen and this one can grab a hydrogen. That is why it's a reversible reaction. Depending on which one grabs, determines which way it's going to go. Lone pair positive charge, let's not forget that. For the direction to go forward, I want this to leave. And so I need to protonate it. And so if I grab a hydrogen like that, that'll now give me this one protonated, which means I only have 1 lone pair, 2 hydrogens, and a positive charge. And now this is my good leaving group. So this is a 2-step. It's the OR, loss of an H+, the OH, gain of an H+. This is happening as a proton exchange with the solution. Yes, reversible arrows. Thank you. Let me tell you, when I did the mechanism video for my YouTube channel, the short one that I have, I had to redo about half of the video because I kept putting in single arrows, and my editor had to go in and just clean them out and put a reversible for each one. So thank you for catching that. I want the notes to be correct when you review them later. All right, so let's go back. So that I showed in one quick step. That is how we got water as a good leaving group. So right now it leaves because the OR is kicking it out. Let me know if this is clear based on me showing it to you like this. Just remind yourself on the exam, double-headed arrow, like as your last step before turning in your exam, just ask yourself, did I get all the double-headed arrows that I need? And if not, go back and make them all reversible. So we are going to focus on this topic today, but I try to do a live stream every Monday. I know today's not Monday because it's been a rough week, but every Monday through finals is my goal unless there's a holiday or something going on. All right, so now that this is clear, why is this important? So we talked about acetals and the mechanism, and yes, you have to know it, but it's not just about an acetal. There's a very, very crucial reason for you to be able to know this reaction. And let me see shortcuts in the comment if, well, you know, I'm going to give you a shortcut, right? So put shortcut in the comments and I will explain why we need to know this. We already talked about the fact that the carbonyl is reactive. We talked about the fact that the diol is reactive. What I didn't tell you is that when I form an acetal, or in this case, a ketal, this thing is not very reactive. If I want to react this thing, I need a strong acid. So why is it important to have one that's reactive turned into something not reactive? You'll see these reactions in the next chapter, but your professor will find a way to throw it in now as well, just because your professor is a professor. Say I have something like this, and I want to do a reaction where I only attack here. Let's say I want to use a Grignard. There is no way this carbonyl is going to be spared. It is susceptible to attack as well. But what if I take this molecule and then I hide the carbonyl from the Grignard or my nucleophile or whatever it is I'm about to attack? I don't let that attacker see that I have the carbonyl, do my reaction, and then bring it back. So for example, in the case of a Grignard, let's say I'm looking for a product that still has my carbonyl intact, but then I want to have, let's see, I want to have something like this with, say, this craziness going on. There's no way to do this unless I hide this. And the way to hide this is I want to hide it. I want to protect it. And the protection that I want to do is turn it into an acetal, or in this case, a ketal. So what I will do in a situation like this is I will take that carbonyl, I will turn it into an acetal, and then I'm going to react it with a Grignard, which I haven't shown you, but that's going to be the next thing we work on. So we'll do this thing right here. That'll give me a molecule that now looks like, well, why am I doing that? It's too much work. Let's do that. Okay, the Grignard attacks. What I get now is my two incoming groups that I wanted. An OH, that's step 1. Step 2 is going to be H3 plus. And then I'm going to use a strong acid. So technically, I'll show it like this. Don't worry about these steps just yet. We'll do the Grignard in a moment. This is why you need the acetal. So let me see. Shortcut in the comments. Excellent. Here's the shortcut. First, let me show you the protecting group that you're most likely going to see. If I have a carbonyl and I react it with two R groups, so let's go with an ROH in excess, then what I get is an OR and an OR. Well, if those R groups happen to be attached to each other, then it's just one molecule, right? You're still good. We're about to start a new reaction, so you're not going to be lost at all. Well, maybe a little bit, but I recommend sticking around and then catching it again later. This right here, if I use a very specific molecule, and let me know in the comments if you're taking the ACS, because you have to know its name, its structure, all the good things. Ethylene glycol is the protecting group that you typically use. Instead of two alcohol molecules, you're going to react with one diol, that is an alcohol, two carbons, and another alcohol, and your product will look something like this. New bonds to the O. These are attached. Look at that. It's wearing a gas mask. It is nice and protected. The Grignard won't see it. Look at that. 2 seconds after joining late and you're already on fire. I love it. That's why I want you to stick around. The gas mask, this right here is your acetal protecting group. This is called ethylene glycol. I think, hold on, ethylene glycol. I think it used to be an antifreeze or something. I may be mistaken. Don't quote me on that. But that's the molecule that you have to know. And shortcuts. Who does not want a good shortcut? If you have to put on an acetal, specifically the gas mask, here's what you want to do. One, break the pi bond, redraw the molecule. Well, actually, don't break the pi bond. I'm so used to saying break the pi bond from all the other reactions. Don't break the pi bond. Let's try again. You want to cut off the oxygen completely because that's the water leaving group. Redraw your carbon skeleton. Put a new bond to an OR on either side. So we have a new bond to the O. And if it happens to be ethylene glycol, then you protect them, connect them. If not, you just put the two R groups like that. And that is the shortcut. I see antifreeze. Yes, thank you for confirming that. And back in the day when antifreeze was used more commonly, if someone had an antifreeze poisoning, like if a child or a pet accidentally got into it, you know what they used as the antidote? Let me know in the comments if you do while I show you the shortcut for reversing it. If you're given an acetal, actually, let's do a protecting group, and you want to remove it, here's the shortcut. So I have my protecting group. Very simple. Well, first of all, the mechanism is in acid. Acid is how you break it off. Break the oxygen bond, redraw the carbon skeleton, and just put your carbonyl in right there, like that. What they used against antifreeze was alcohol, just drinking alcohol, because if ethylene glycol bound to receptors by two alcohols, alcohol and alcohol, drinking ethanol would displace it, and that would make the kid drunk. But a drunk kid is better than a dead kid, so that is what they used. And that was very, like, people were told, because I worked in EMS, and I think they were phasing it out at that time. We were told alcohol will make the kid drunk, but at least, you know, keep them safe. They were getting kids drunk. Oh my goodness. Look, I didn't realize how scary all these things were until I had a child, and now I'm paranoid about everything. All right, so let me know in the comments if you're good with the shortcuts. Oh my goodness, we're an hour in. Okay, let's take a quick vote. Skip Grignards and call it a day, or keep going, because why not? Congratulations, Jackie. Congratulations. That is awesome. EMS was one of the most exciting things that I did during college. It was a lot of adventures, we'll put it that way. An hour has flown by. Yep. Yeah, so I had this should be a 45-minute lesson outline, but I still have more things, and I see keep going, please keep going. All right, let's do it. If anyone is tired, just catch the recording later. It will be waiting for you on YouTube. Don't forget, worksheet in the comments if you want the worksheet, live notes if you want a copy of the notes, and that way I've got you covered before you leave. Leslie has an exam Thursday, so keep going. Awesome. Well, Leslie, let's get you acing your exam with one of my favorite Orgo 2 reactions. You've heard me talk about it in all the other sessions. So the challenge, since we're past the hour, will you give me a chance to make it your favorite reaction too? Let me know yes or no in the comments. And that reaction, many people cannot pronounce. For fun, ask your friends to pronounce it, is the Grignard reaction. Grignard, not Grignard, Grignard. And I see a lot of yeses. Awesome. So let's go. I love the Grignard because it's so versatile for when you want to do a chain elongation. There's a lot of tricks that you can use with it, and it's great for synthesis. The thing about a Grignard is that it makes a carbon act like a carbanion. Carbon does not like a negative charge. So if you have a carbanion, because it's bound to an MgX, for example, MgBr, it's a very partially positive, very partially negative. This thing is so partially negative, that right there is as if you have a carbanion. As if, not an actual carbanion, as if. And that will attack, which is great for chain elongation. And there are so many patterns that you can follow to recognize, hey, carbanion, Grignard. The basis of a Grignard reaction is that the carbon attached to the Mg is very, very strong. It's considered negative, but it's not a C minus, it's C bound to something. And when we look at a nucleophile, when we look at a carbonyl, like an aldehyde or a ketone, the Grignard will come in and attack much faster and much stronger than any of the nucleophiles we looked at before. So it'll take its electrons, attack right there, kick it up, and our intermediate will be an O minus. We have the extra lone pair over here with a negative charge. And I just added a carbon to my chain. Just clean, no anything in between, no OR, no NR. It's just a carbon, and I made the chain longer. And if I don't like having the oxygen there, if I just want a clean chain elongation, let me just show you the next step. We need protonate with H+. Then I can do a reaction that completely removes the alcohol, which if I want to, I can, but it's an option. It just opens a world of opportunity. The mechanism is very easy, and the uses are very, very important. But first, what happens to the MgBr? Once it's broken off from carbon, it is a spectator ion in solution. It doesn't matter anymore. It tends to hang around the O minus initially because magnesium has that positive charge. But once you protonate, then it gets surrounded by the polar protic solid, and we don't care about it, so we ignore it. Making our first baby Grignard was super fun lab. Oh, I have bad memories of Grignard lab. I love the reaction on paper. I did not like my lab professor. A zillion years ago. When did I take that lab? 2005? Oof. All right, Grignard reactions are done in very dry conditions in the lab. Yes, and let me show you why. If I was crazy enough to try to dissolve this reaction in water or alcohol to make it wet, then any water in solution would get attacked by the Grignard immediately, and there would be no more Grignard. So it has to be dry because you don't want the Grignard to be completely destroyed before you even get to do a reaction. OMG, okay, now I'm actually loving the Grignard. Well, Scotty, hold that thought. You want to see some shortcuts because the shortcuts, I think, is what make it even more exciting. The mechanism is easy, but as easy as it is, you don't want to take your time drawing a mechanism if you don't have to. So you know the drill. Shortcut in the comments if you want some goodies. Here is my starting molecule, and I am asked to somehow, some way convert this or react this with something that looks like this. MgBr in step 1, step 2, H3O+. I somehow always seem to write MgBr, but you can absolutely use chlorine as well. I think iodine is not as common. I think it's something about iodine makes it not ideal. I don't remember why, but MgBr just happens to be what I go with. You can use MgCl as well. The mechanism, sure, we don't have time for it, so here's the shortcut. Break the pi bond. Redraw the carbon skeleton exactly as you see it, but with a single bond to the oxygen. Add a hydrogen to the oxygen, turning it into an alcohol. Add a new bond to the former carbonyl carbon, and then add that new R group that you just brought in. Now, this looks a little bit wonky. Professors will try to make it look more like a longer chain, so let me just redraw it. This right here, new bond, incoming group. Don't forget that this carbon has a methyl group and an OH. It's just a redraw, so I'm going to put redraw so you're not confused why I have it twice. Don't be thrown off by it being drawn differently. It's just like that. Let's look at some patterns for the aldehydes and ketones. If I start with an aldehyde versus, let me see how much room I have, versus a ketone, and we'll do the same exact starting molecule, and I react it with a Grignard. We'll use an R, MgCl, reminding myself not to use bromine all the time. Break the pi bond, put a hydrogen there, put the R group, let me put it a little neater, put the R group here, like that. All right, so let's redraw it. For the aldehyde, I have my hydrogen, my oxygen. I put it in green, so I'll have an O, and then I have an R. Let's make the R an actual group because I want you to really see what I'm doing here. So let's make it an ethyl Grignard. And that would give me just the longer chain like that. If I do this with a ketone, then I have the ethyl adding in. And let's not forget, I have the O getting mixed up my colors. The O was blue to begin with. And if you wonder why I'm so OCD with the colors, I have ADHD. Can you imagine if we did this the way most professors do? And we had an entire session like that? I would lose my mind, and I already know this. I can't imagine how much more confused I would be if I didn't know it. And so this helps me focus, and hopefully it helps you as well. Here's the pattern. I had an aldehyde. I created a, notice my alcohol is secondary. I had a ketone, and I created, notice, a tertiary alcohol. If I start with formaldehyde, because Aishan, I think it was you or Scott, was it you who asked about it earlier? If I have formaldehyde, form tells me it's just one, which means it's an aldehyde with two hydrogens, a very unique case. Then I don't want to just tell you what to memorize. I want you to pay attention. I add one R group. So if it's an aldehyde that has an R group, it goes secondary. A ketone has two R groups, it goes to 3, tertiary. But if I have no R groups, then it goes up by 1. I get a primary alcohol. So I have my carbon, right? We break it, hydrogen, R group. So that means I have my O, H, R group. That's an ethyl. I should probably show what I'm doing here. There we go. And that, well, let's not forget the 2 hydrogens so that this thing has a complete octet. Formaldehyde will give you a primary alcohol. So do you see the pattern? I have nothing, it's primary. I have 1 R group, it's secondary. 2 R groups goes tertiary. Ishan, since you asked for it, let me know if this is what you were hoping for and if the shortcuts help. Yes, absolutely agree. Wow. I guess we are all on the same page. Excellent. So I see we have the primary alcohol, propanol, absolutely correct. Excellent. All right, but there's more. Let's keep going. What if you are given the product and you're asked to show what it came from? So let's not make it easy because your professor won't. And you're asked to show how I made this from a Grignard. So this came from what? Here's the trick. You are going to identify the carbon that is holding the oxygen. That was your carbonyl. So get rid of the hydrogen. And then we have options. I can break on this side, or I can break on this side, means I could have used 2 different sets of molecules to get to this point. Let's start with the light blue side. Where I break, I put an MgX on that side. So for this one, this would have come from, up arrow, because it came from here. I have my benzene ring, and I did the ring on purpose because, let me know if you agree, your professor will teach something simple, put a ring or an aromatic group or something on your exam just to make it scary, when in reality, it should just be the same thing. So I put the rings in on purpose to have you realize, oh, I can do this regardless. On this fragment, I have 1 carbon, and on that carbon, I have to put my MgX. I'm not seeing this color as clearly, so I'm just going to make it darker. There we go. Let's make that actually very clear. So MgBr plus the other fragment is a 3-carbon chain with an O and the H. that I just added. So that is my, wait, what am I doing? Not an H, it's a carbonyl, right? That's where it came from. The Grignard attacked the carbonyl. Option 2 is this one, where I break it at the orange line. That means this is my carbonyl, and that is my Grignard. So let's start with the benzene ring, and it has 1, 2 carbons attached. 1, 2. That second one is the carbonyl, plus I have an ethyl with a Grignard. 2 options, or, and your professor may ask, give me all the different possibilities that I could have used to create this. And there you go. All right, we are definitely out of time. Let me know if you want to do at least one synthesis, and then on the worksheet, I'll make sure that you have a couple more synthesis questions. Let's see, OMG synthesis, please. Something phobia is the fear of palindromes, which is ironic. So we need, oh, because you said cyclophobia first. I did not, oh, I missed all the comments. Hang on, I missed a whole bunch. Have you ever taught OChem as a professor? No, and I have a very, very good reason for that. How many students here like to go to class and look forward to their professor lecturing? Most don't. You are here because you want to. Nobody here is here because of their grade, because I'm not grading you. You are here to learn, and that means I enjoy this. I would hate to go to class and have my students steer daggers at me on a daily basis. I'd be miserable. And the schools also probably would not like my style. I'm too childish, but I like it. Okay, so retrosynthesis, cyclophobia, yeses to synthesis. Awesome. All right, let's do some synthesis. So more bedtime in 20 minutes. But let's keep going. And I say that because my kid's going to be up in a couple of hours crying for some excuse or other. We got him this clock called OK to Wake, and it turns green. I set it to whatever time it turns green. And the idea is you can't wake up until the clock is green, which in theory sounds good, but he translates it to, if the clock is red, I'm going to come crying to mom and daddy's room. And if the clock is green, I'm going to come happy into mom and daddy's room, and then just wake us up regardless. So we're working on that. All right, as I was talking, first synthesis problem, how would you approach something like this? Jackie, thank you. I appreciate that. Leslie, let's do it. You have an exam coming up. Let's make sure you, wait, you said Thursday. Did you mean tomorrow? Jackie, does the little girl also translate, what moods do I come into mom and daddy's room? All right, so just because we're dealing with more difficult synthesis does not mean you should abandon what we have done before. So if you go back to my synthesis session, I tell you to start with busy work so that you're on the right track so you don't get overwhelmed. And the busy work is question number 1, what is the same? And question number 2, what is different? And that's how we're going to know what to do. What is the same? Well, let's see. I have 1, 2, 3, 4 carbons, and here I have 6. So 4 of the carbons are the same. 2 more carbons are different. And I also turned the carbonyl into an alcohol. Here is the clue I want you to recognize. Okay, thanks for clarifying that. If you notice that the difference is an addition of carbon, a chain elongation, and an alcohol, your clue is right there with chain elongation at this position. And the alcohol is the result of using a Grignard. That is going to make it so easy, because the moment you notice you have a Grignard reaction, you turn that carbon to oxygen to a carbonyl, get rid of that, break it right there, 1, 2, 3, 4. Let me know if what I did really fast now just made the light bulbs go off. And that is my Grignard. Did you see how quickly it just fell into place the moment I noticed the Grignard pattern? And if you did, well, this is very easy. It's not even a multi-step synthesis. It's a one-step synthesis. All I have to do is react it with an ethyl, Grignard, step 1, step 2, H3O+, and I am done. Stylish drop. Okay, let's try. Let me show you another pattern, which is really exciting. Let me think for a moment. Okay, we're going to go a little bit evil now. This is not in my notes, so give me a moment to make sure I get all the pieces right. Ooh, I can make this really evil. Okay. Another reason you would not want me as your professor is I don't do easy when I'm trying to test you. So I want that right there to go to. Hold on. Just bear with me. All right. What do you think? Easy, medium, or hard? Okay. Here's the problem. You know there was a Grignard. Oh, I accidentally made it easy. No, I didn't make it easy. Okay. Here's the problem. You can't use the trick from earlier because if you did and you turn this into that, that would be a good way for chain elongation. You know what? No, this is too easy. Hang on, hang on. Yes, yes, I do believe it's easy. Bear with me. I want a different problem. I want that. That is harder. No, no. Hold on. There we go. Did that just make it harder? Sorry, Jackie. Once you realize the pattern, I realize I accidentally gave you this pattern. I'm trying to show you a different one. So now I can't simply say cut it right there because I'm starting with a 5-carbon chain. 1, 2, 3, 4, 5. So if I'm looking at my questions, for question 1, what is the same? And question 2, what is different? And I say that this carbon chain here, that this is the light blue, then all of this has to be light blue. The only place I can cut it is here. I cannot use that trick. And what I accidentally gave you was a molecule where you could have cut backwards. That's why I said it was easy. Now I can't cut it that way. So instead, I want to realize a different pattern. Here is what I want you to look for. Ready? If you have a carbon chain that grew 1 carbon away from the alcohol, not the alcohol, 1 carbon. Oh, I'm in the wrong chapter. We're going to do this anyway, but this is not an aldehyde ketone. I got carried away with the Grignard. But if you learned the Grignards as a separate chapter, then bonus question for you. The pattern is an epoxide that was opened with the Grignard. I outsmarted myself. It is very late. All right, that's the trick. Totally didn't mean to do this one today because that's a different chapter. And because of that, I will fly through the synthesis as follows. If I know that came from an epoxide, I need to make an epoxide. So step 1, I'm going to eliminate to get an alkene. I will turn that alkene into an epoxide. I will then attack the epoxide with a Grignard, and that would be this thing right here. Step 1, step 2, H3O+, and then fill in my reagents. Terminal, which means I need to use tert butoxide. Don't forget about tert butoxide in Orgo 2. I had so many students forget them. How do your professors like to put HOTB, potassium terpenoxide, and HOTB. That's a tricky way to put it. And then MCPBA, that's your peroxy acid, metachloropurbenzoic acid. I have this. I reacted with the Grignard. Accidentally put this in today. See, that's why I write my notes so that I know which problems to give you. Let's end with the one that I actually did have on my notes for today because that's relevant to this chapter. So this molecule right here, going to, let me know if that last one was helpful, considering that it is nowhere near an aldehyde. I just got excited. I want to form something like this. Easy, medium, or hard. Good refresh. Excellent. All right. Easy, medium, or hard. I see. Medium. Okay. I like it. Medium is good. And so what we're going to do here is, well, we're going to ask her questions. 1, what is the same? And 2, what is different? Did you notice for a moment that I forgot to do the opening questions? Then I started looking at it and my brain is thinking, what on earth do I do? The questions help jumpstart my brain. That's why I recommend always starting with those questions. What is the same is the fact that I have this thing right here, but not the pi bond. The pi bond is new. And that's a carbon ring, a cyclohexane with 2 carbons. So that is this and that. Whoops, wrong color. So what is different, I'll just put blue. What is different is the fact that I added 2 carbons. Well, 1 carbon, sorry. 1 carbon and an alcohol. So it's plus 1 carbon. And I have a C double C going to an alcohol. It's not as obvious as before, but there are 2 things that I did. If I do these 2 things, I immediately want to think Grignard. 1 is a chain elongation. I'll just write chain elong. And 2 is I have an alcohol or some kind of residue that used to be an alcohol. Ooh, let's make it harder. Let's make it harder. Okay, what do you think? Is this problem harder than the one I just showed you? I kind of gave it away, but is this harder? Here's the thing. These 2 things still apply because if I have an alcohol or a group that came from the alcohol, so if you remember that you can dehydrate an alcohol, then you can think, oh, that right there could have been an alcohol. And now I have my clue for a Grignard because I can do, let me just redraw it here so you can see. If I have this right here with an alcohol, cut the hydrogen, make a carbonyl, that's where the chain grew, MgX on there. If I have not an alcohol, but the chain grew, can I have made it from an alcohol? Yes, I can. 1 step back, I could have had something that looked like this with the alcohol. I did an elimination to give me, so let's not show that right there. Yeah, we can kind of hint that we have the alcohol. But if I have the alcohol and I eliminate it with an E2 reaction, then I can easily get the product that I'm looking for. And now I can apply the shortcut. Cross out the hydrogen, make it a carbonyl, break it right there. And that right there gets an MgX. So let's start making this thing. I need to have a terminal alcohol. And so I will use my Orgo 1 reaction. Remember in the beginning of the session, I said professors will keep using the Orgo 1 reactions. If I have this as an alcohol, I then turn, why am I turning that into an alcohol? Hang on. Yes, because I want a carbonyl. So I need to go, I forgot that we have that extra carbon that we need to add first. Lost myself there for a moment. I then turn it into a carbonyl. So we'll use PCC. I forgot to mention this when we talked about oxidation. So let me go back real quick. Where did we talk about oxidation? No. There we go. Okay. The aldehyde will not be isolated. Most of your oxidizing reagents will go all the way to a carboxylic acid. The only one that stops is PCC. P for prude, it doesn't go all the way. The rest, any strong oxidizing reagent will go all the way. So strong oxidizing reagent. And PCC is the only one that will stop right there, which is important because we need PCC right now to give me just the aldehyde, not the carboxylic acid, because the carboxy would destroy the reaction. I then take this right here, react it with the Grignard. I only need one more carbon, so I'm going to use a CH3MgBr. That's step 1. Step 2, I'll add some H3O+, and then we're going to need another step here. So kind of squeeze myself into a corner. I cannot simply take that alcohol and get rid of it at the terminal position because an E1 reaction with acetic acid is not going to work. So that would give me a carbocation. It could potentially go here, rearrangement, no good. What I need is to kind of take a side step and give me a different leaving group that I can eliminate. So we'll swap it for something like a bromine using PBr3 or SOCl2 for a chlorine. And then we can go from there and turn that into the pi bond using tert butoxide to eliminate at the less substituted position. So most students don't learn the niche reagents. They tend to focus on the big ones like the chromiums and the acids or KMnO4. And so we're just going to stick to the basics. But if your professor is teaching extra, make sure you know what they are or what they do. You are very, very welcome. Awesome. I look forward to seeing you next week. Yes, PBr3, perfect. Yes, so what you gave me is correct if we wanted a more substituted position, but in this one we don't. What would you use for the first step? Okay, let's go back to the reagents. For this one, I would use BH3 and THF. Step 1. Step 2, NaOH and H2O2. Remember the alkyne that we did that gave us an enol? Same idea, anti-Markovnikov alcohol addition, PCC, Grignard, sidetrack here to get a different leaving group, and then we are good to go. But that's a good thing to know them, absolutely. So at the end of, I was a bio major, and then after organic chemistry, I walked into the chem department and I said, I told her, I want to sign my soul over to the devil. She looked at me, what are you talking about? I said, I want to add chemistry as a second major. All right, so that is just the start. Now, I know it's a lot to process, but as I said, I've got you covered. Comment live notes for a copy of today's session notes and worksheet for even more practice for the brand new aldehyde and ketone worksheet.